My name is Simon Marlowe. I work at Facebook, and I'd like to tell you about Haxel. So first of all, to set the scene, let's talk a bit about I/O. So sooner or later, when we're writing programs, we have to write programs that interact with the real world in some way, and that involves doing some sort of I/O. But I/O brings with it a number of problems. First of all, it tends to be quite slow. So when we're doing lots of I/O, we like to try and overlap it as much as possible using some kind of concurrency. Secondly, I/O tends to be hard to test because the next time you do the I/O, it might give a different result because it's interacting with the real world. It might have changed the world, or the world itself might have changed. So it's hard to build reproducible tests. Thirdly, it's hard to debug because when you've got a failure and you try to reproduce that failure, the code that you ran might not give the same result because the world has changed again. So debugging problems that occurred in production or occurred on a customer's machine might be quite difficult. So these three problems might not seem related, but I'm going to tell you about a framework that helps with all three of them. But maybe what you're thinking is, what are you talking about, Simon? I know how to solve these problems, right? I've been doing this for a long time. I write code all the time. I do concurrency. I do testing. I know how to solve these problems. And you're probably right. For example, let's look at concurrency, right? Every language has some kind of concurrency. And these programming models like async await are quite popular these days, particularly for doing overlapping of I/O. But then there's also threads and futures and actors and all the other different kinds of concurrency that we have available. We have a wealth of different ways for doing concurrency these days. But these aren't ideal in all situations. In particular, I have to remember when to use concurrency. So I've got to look at my code. I've got to find the places where I can overlap the I/O, and I've got to explicitly use some kind of concurrency. And even if you do that, there are ways that you can still go wrong. So with futures, you can wait too early, for example. You can write concurrency in a way that isn't optimal for the available concurrency in your program. And then, even if you do it, the concurrency has cluttered the code. So you're mixing up the functionality of your code with the operational details of the concurrency. And then when somebody comes along later on to refactor your code, they've got to, or they may have to change the dependencies, which may lead to changing the concurrency and the structure of the concurrency in the code. And then refactoring itself, of course, is harder because you've got all this extra structure in the code. So maybe we shouldn't have to do this, but you're probably thinking, well, but I have to do this because there might be side effects, right? So I can't just have rampant concurrency in my program because the side effects might interleave in some non-deterministic way, and then I can't tell what my program is doing. And again, that's absolutely right. But many of the cases, many of the programs that we write have parts where we're insensitive to the reordering of operations. So for example, if we're gathering data and then making a decision based on that data, the parts where we're gathering the data, we don't mind particularly if we're doing multiple database accesses and those database accesses get reordered or done in parallel or whatever. We probably don't mind about that. And then we can make the decisions. And this part of our program is really side effect free in a sort of moral way, right? It's not technically side effect free, but it's morally side effect free because we're happy for things to be reordered. So lots of things fall into this kind of category. For example, rendering a web page. So if you hit your web application and it goes and fetches some data from the databases and the services and so forth, and then it generates some HTML and sends it back down to you, all of that fetching the data and generating the HTML, all of that was really side effect free, and we could have just exploited all the concurrency that was available. So the thing I'm going to claim here is that when there are no side effects in the parts of your program that have no side effects, concurrency is probably a better default than the sequential default that we have right now. So what about the other two problems I told you about? How do we go about testing our I/O code? Well, you can just sort of run it, and if it does the right thing, well, maybe it'll do the right thing when I actually push it into production, it'll be fine. So obviously that's not always the best way to do it. It leads to test plans like this that say, oh, well, it sort of worked on my machine, so I guess it's okay. How can we do better than this? Well, the problem is I/O interacts with the real world, so we have to figure out some way to build a reproducible test case. So we could reserve part of the world for testing, maybe some little bit that you don't mind about too much. And So you could have a test database, for example. And that's okay, but you've got to make sure that the world is working well enough for that test database to work. You've got to make sure that the test database is representative enough of the rest of the world when you want to run the code for real. And you've got to make sure that your test, when you run it against the test database, doesn't accidentally go and modify the real database. And that has happened, I believe. So that's one way that we could do it. A slightly better way to do it is to somehow fake the world. So wrap your test in some kind of pretend world that behaves exactly like the real world as far as the test is concerned, so that we can test our code against the fake world. And usually this is what we call a mock API. So we take some APIs, the APIs in our program that do the I/O, and we create a mock version of that API. But then we have to populate that mock API with the test data somehow, and we've got to get some test data from somewhere. So where do we get the test data from? Well, we could write some code to generate the test data, but that's sort of hard work. And obviously we can't write the test data by hand, that's even harder work. What we'd really like to do is to run the test against the real world and then capture all that data and then use that to replay our test over and over again. But building these mocks that can record data and then replay it later is quite hard work, and we have to do it for each different kind of I/O that we've got. So this is kind of the state of the art, but it's still hard work. What about debugging? So what happens when something goes wrong in production or on your customer's machine or whatever? How can you reproduce that failure and try and diagnose what happened? Well, usually what we do is we add lots and lots of logging, and we capture all that logging, and then we try and figure out what happened. But this is not a great solution either, because, again, you have to remember to do it, and you have to anticipate all the places where you should log stuff just in case something goes wrong. And if you didn't get it right, and you got a failure that isn't described enough by the logging to be able to diagnose it, you have to add some more logging, and then you have to get that back into production, and then you have to hope that the failure reproduces again, and then go around this loop, hopefully not too many times. And then the logging clutters all the code, so you've got all this logging spread around your code. What we want to happen is to just get the failure and be able to reproduce it and diagnose it. That's ideally what we want. So let me take a little digression for a minute and talk about a class of tools that I like to call big hammers. So the characteristics of a big hammer is that it takes a hard problem and just makes it go away. Right? It just solves some hard problem, makes it go away. But these things are often, because these problems are so hard, you have to go to some effort in order to use the big hammer. So you might have to change your workflow, you might have to write some boilerplate, or go to some extra work in order to use the big hammer. So this is a bit abstract, but let me give you a few examples to give you an idea of what I mean. So the first one that came to mind was distributed source control. So I come from a time before this, where we used to email patches to each other on mailing lists, and it was not very fun. So nowadays, of course, we can exchange changes with each other very easily. We can track lines of development. We have a wealth of information about the history of our projects, and this has just revolutionized the way that we do collaborative software development. But you have to go to some effort to use it. You have to commit your changes, you have to write commit logs, you have to track branches and so forth. But we all do this because it's worthwhile. Secondly, garbage collection makes the problem of memory management go away. Well, it doesn't completely make it go away. It gives it to the JVM team in your company or something. But by and large, for the programmer, it makes the problem of memory management go away. Language-independent RPC is very useful if you have a large ecosystem of software and you want to write things in different languages. And the idea of language-independent RPC is that you just specify your types and your services in one language-independent way, and then you compile that into different languages. So then you can access all of your services and all of your data from components written in different languages. So this just makes your ecosystem able to scale in lots of different ways and lets you choose the best tool for the job. And you can see where I'm going with this. The big hammer that I'm going to talk about is a thing called Haxel. Now, what is Haxel? Well, Haxel is a Haskell library. And the point of Haxel is that it provides an abstraction over concurrent I/O. And it works in conjunction with a compiler extension that we developed called applicative do, which is in the Haskell compiler. It was released in GHC 8.0. And so let me give you an example of what Haskell can do. So I've chosen, as an example, a script, a kind of DevOps-y type script that you might run on your network. And it's going to look at a bunch of machines and update software on those machines. So I need a little API. First of all, I need a function called getLatestVersion. So getLatestVersion is going to query the software database for the latest version of some software. And it's a Haskell computation that returns a version. This is its type. If you don't read Haskell, the blue bits are the types. Next, we have a function called getHosts. And getHosts is going to find out the names of all the hosts on the network that I need to run my script against. So it's a Haskell computation that returns a list of hosts. The next function is called getInstalledVersion. So this is a function that takes a host and it returns a version. It queries that host for the version of the software that's installed on that host. And finally, I've got a function update2, which performs an operation. It takes a version and a host, and it updates the software on that host to the version that you give it. And it doesn't return a result. So here is the script. So it's a do expression in Haskell, and do introduces a sequence of statements. Each of the statements has the operation to run on the right-hand side, and on the left-hand side, the variable that we're going to bind the result to. So this is running getLatestVersion and binding the result version to the variable latest. Next, we run getHosts, and we bind the result to a variable hosts. Next, we're going to call getInstalledVersion on each of those hosts. So I'm going to map the getInstalledVersion operation over the list of hosts, and I get back a list of installed versions. Next, I need to figure out which of those hosts I need to update. So I've got to look at each of those hosts and the installed version on that host, and build a list of hosts that have an outdated version. So this is a list comprehension. It's iterating through the zip of the hosts and installed lists, and every time we find a version that's less than the latest version, we put the H in the list. So we end up with a list of hosts that have an outdated version. And finally, when we've got that list of outdated hosts, we can just map our update2 operation, passing it the latest version to install onto those outdated hosts. So this is the complete script. And that's more or less exactly what you want to write. But some parts of the script could run in parallel. So which parts? Let's look at the dependency graph of these operations. So this graph is just representing the data dependencies between the various operations in the script. And you can see that getting the hosts and getting the latest version have no dependencies between them, so we could be doing those things in parallel. And once we've got all the hosts, querying each of those hosts for the installed version is also something we can do in parallel across all of the hosts. And finally, doing all the updates can be done in parallel across all of the hosts that need updating. And the nice thing about Haskell is if I just run this script in Haskell with the applicative do compiler extension, it will actually execute the program according to this dependency graph, and it will do things in parallel as far as possible. How? Well, so the data dependencies determine the ordering rather than the sequential statements that we wrote. The compiler is going to look at the data dependencies. And when you have independent computations, those will happen in parallel as far as possible. I didn't write any explicit concurrency constructs at all. So there was no fork, there was no async, no await, none of that stuff. Just a sequence of statements with dependencies between them. And so the slogan is that you get the code, you get to write the code that you wanted, and you get parallelism for no extra effort. So just like in garbage collection, we abstracted away from the memory management, in Haskell, we're abstracting away from the concurrency. And I'm not saying that both of these methods do a perfect job, right? In garbage collection, if you did the memory management by yourself, you could probably do a slightly more efficient job than the garbage collector. And in Haskell, if you were prepared to do the scheduling yourself, you could probably do a better job than Haskell too. But if you don't mind getting 80 or 90% of the way there, you can get there for very little effort just by using the big hammer. Or to put it another way, what we did here is we flipped the default from sequential to concurrent. Instead of everything being forced to be sequential and having to say which things are concurrent, everything is concurrent unless you say so, or unless you have a data dependency. And this makes a lot of sense when concurrence is the right default in the parts of your program where you don't mind reordering things. You would just like concurrency to happen. So perhaps you're wondering how it works. Well, the problem is, first of all, that data dependencies are not first-class things in our language. So we can't talk about data dependencies in a library. So I can't write a library that does this. I have to get the compiler involved somehow. But I don't want to build all of this functionality into the compiler. Somehow I've got to find some more abstract way of doing what I need to do. So let's look at a fragment of this example that we talked about. We had these two statements, get latest version and get host, and they're independent of each other. But only the compiler knows that, because only the compiler can look at the variable names and see where they occur. And the compiler, when it sees this statement, this is actually syntactic sugar, the do statement, and the compiler expands it into a larger expression using the monad bind operator. And every monad implements the monad bind operator. This is how the do syntax does different things depending on which monad you're using. And that's fine, but the problem is that we've already lost as far as parallelism goes here, because the monad bind operator incorporates into it the idea of sequentiality, because it takes two arguments, a computation on the left that returns an A, and a computation on the right, or sorry, a function on the right that takes the A that was returned by the left. So we can't do the right thing until we've done the left thing. So it forces sequentiality. So the monad bind operator is the sequential composition. And that's not what we want. This can only be sequential. We've already gone wrong if we've translated the expression into this monad expression. So we need to use a slightly different abstraction. Unfortunately, Haskell provides a thing called applicative. So applicative is another way of combining computations. And it uses this operation called app, or sometimes we call it splat. And this is kind of a parallel composition of things. So it combines things in parallel, as long as the implementation of this operator can exploit that parallelism. And the reason it can do that is because the two arguments to the splat operator are independent. The left is a computation that returns a function, and the right is the computation that returns a value. And then finally, the function is applied to the value. But this is all very well, but I don't really want to write this thing by hand. It looks a bit like line noise. And I've also had to still figure out which parts of my program I can do in parallel in order to write it in this form. So I don't want to write that by hand. So what we did is we added an extension to the compiler called the applicative do transformation. And applicative do looks at the program, looks at each of these do statements, and the dependencies between the statements in the do block, and it translates it into the applicative style as far as possible. So it tries to extract all of the available parallelism between the statements and embody that by expressing it in the applicative style. That's the first part. And then the second part is that the Haskell library implements the splat operator in order to give you the parallelism. Well, what do I mean by that? How does it implement this operator to give you parallelism? Well, that was the first transformation. Then the second part is that Haskell is going to evaluate this computation in order to find a list of things that it can do in parallel. And then it will give that list of things that it's doing in parallel to the back end. And it's your job to provide the back end. So Haskell doesn't embody any particular kind of I/O into it. You have to say how to execute your I/O. And this function fetch that you provide is passed a list of operations that Haskell extracted from your code. And given a list of operations, of course, you can choose how to do them in parallel. So you can choose to just overlap them all using threads, or you could choose to, perhaps you can batch them together and send a single request as a single batch down to the database, or use any kind of mechanism that you want to. But the point is that you provide the fetch operation. Haskell's job is to run your code and extract all of those operations, and then give you the list that you can do in parallel. So the overall effect of doing this is, if you think about the structure of your code as a dependency graph, where the nodes are the I/O, Haxel is exploring this dependency graph in a breadth-first way. So it's finding a list of things that it can do in parallel. Then it does all those things in parallel, and then it carries on running the computation again because the results have unblocked more of the graph. Now we can explore more of the graph, then we find more I/O, and we keep on doing this over and over again until the whole thing is finished and we have an answer. So what about the other two problems that I talked about? I mentioned testing and debugging. So in order to use Haxel for your I/O, what you have to do is you have to make a data type for each of the different kinds of I/O in the program. So here's an example where I've made a data type for doing an HTTP request. And then once I've made the data type, I have to add some boilerplate instances for various things, and I have to implement that I/O by providing the fetch operation that I just talked about. And in this case, so fetch is just going to take the HTTP data type and it's going to pass it off to some HTTP request library. So it's fairly straightforward to implement all this stuff. And you have to do that for each different type of I/O. But now that I've done that, all of our I/O is data. And you can do a lot more with data than you can do with pure I/O because you can inspect it and you can compare it. And one of the things that Haxel does with your I/O is that it makes a cache of all of the requests and the responses that have happened in the code so far. And normally we use that in a per request way. If you're writing a server, we start a fresh cache when you get a new request on the server, and then we throw the cache away at the end. So we don't have to worry about data becoming stale. It just lasts for the cache lasts for the period of the request. But now we have this nice property that if you fetch data again, you get back the same result that you got back the first time. And this is, of course, really good for performance. It's also really nice for correctness. For example, if you're writing a web application and you have to fetch lots of data, it's a bit strange if different parts of the page had reflected different data because the data changed underneath you while you were generating the web page. So Haxel kind of avoids that problem because it's making sure that you get back the same result if you fetch the same data again. We've also found that it's really useful for modularity. That's a bit surprising, perhaps. But if you fetch the same data in different parts of your program, in order to optimize that, what you would have to do is find those different places where you're using the same data fetching and extract that into another module and do it first and then pass the results down. But that's created some extra coupling between different components in your program. And now that's making refactoring harder in the future because if you change the program such that you don't need the data anymore, you've got to go back to this shared component and maybe change it. So it's much easier if you don't have to do that. If you just have a cache behind the scenes that's remembering what you fetched, and you're just free to fetch whatever you like, wherever you like in your program, then that means you can keep the components separate and you don't have to worry about fetching things up front. So now we have a cache that's recorded all of the I/O that we performed during our request or during the run of our code. And so having got to the end of our request, we have a full cache that records everything that we've fetched. Now if we run the code again, we're guaranteed to get exactly the same result that we got the first time. And that's because we've wrapped all of the I/O in the code. There's no way that we can have non-deterministic effects happening in the middle. So that's a nice property to have, and we can exploit that. So Haxel gives you a way to dump the cache. It's got an operation called dump cache as Haskell. So when you run dump cache as Haskell, it prints out the cache as a Haskell program, and the effect of running this program is to populate the cache again. So of course you could serialize it in different ways. You could also dump it as binary or text. But this is a really useful serialization format because the compiler is the deserializer. So we've dumped the cache as a Haskell program. Now we have all the pieces we need to make a test. So we run the code, we dump the cache into a file, we commit the file into our repository, and now we have a unit test. Cool, right? And because you can populate the cache programmatically, you can also write libraries that generate test data. So there's a way to make synthetic test data as well. So this is really, really useful. And it's really useful to make the test and to re-record the data when you need to. We use this quite a lot in our system at Facebook. And finally, this gives us a handle on the debugging problem as well. So the debugging problem was that we don't know how to reproduce our problem when it happens in production. But now we can just dump the cache. And provided we have all the other pieces we need, we have the code that was running, we have the input to the request, and we have the cache that records everything that was fetched from the world during the course of running that request. Now I can just reproduce the failure, and I can diagnose exactly what happened when the failure happened in practice. So why did we make Haxel? Well, Haxel is actually used at scale in a system called Sigma at Facebook. Sigma's job is to classify lots of different actions on Facebook and content according to whether those actions or that content is abusive in some way. Spam is one of the main classifications of abuse, but there's also things like malware, other kinds of abuse, fake accounts, and so forth that we try and classify. And all of the different logic that's involved in trying to classify something as abuse is all written in Haxel and runs on the Sigma service. And Haxel gives us the way of running all of these different rules and all of this logic in parallel. So there's a nice blog post that you can read about this on the Facebook Engineering blog. Haxel is also open source, so you can go and find Haxel on GitHub. If Haskell is not your thing, then there's a whole bunch of clones of Haxel in your favorite language, I hope. So at last count, we have about 8 different clones, and these implement really the main features of Haxel, not necessarily all of the bells and whistles that we have. But the idea has been re-implemented in several different languages, including one in Haskell, it turns out, because somebody thought they could do it in a nicer way than we did, which is perfectly fine. Okay, so just to summarize, so you have to write some boilerplate for all of your I/O. So that's the contract, right? So you look at all the I/O in your program, you have to write a data type, and you have to write some boilerplate. You have to say how to execute that I/O. But once you've done that for all of the I/O in your program, then you get lots of nice benefits. You get automatic concurrency, you get caching. The caching gives you testability, automatic record replay. So it's like a mock layer for all of the different types of I/O that you're doing in your program. And finally, you get debuggability, because you can capture the cache, and then you can reproduce failures that happened later on. So I've just about reached the end, but I have plenty of time, and I'd be happy to take questions. Thank you. Yep.
Is it possible that Haxel can run one branch ahead of time if that finishes earlier? So that branch there, is that the top left of the circle finished earlier? Could it advance to the second layer of that computation ahead of finishing all of the other things in that round?
Yeah, that's a really good question. So I'll repeat the question. The question is, do we have to do everything in strict layers like this? And do we have to wait for the complete layer to finish before we do the next part? And actually, we're working on a new version of Haxel, which I'll hopefully release very soon. I'm just testing it at the moment, that can arbitrarily overlap all these different things. So it relies on implementing your I/O in such a way that it, rather than just returning a result, it has to call back later on to tell you it's got the result. But yes, so and we found some nice latency wins by implementing that. So it's able to overlap more things. So that's, yeah.
What drove the team to use Haskell?
A number of different things. Sorry, the question was, what drove our team to use Haskell? A number of different things. So there was an existing functional language that was used as a DSL internally in the system that we were working on. And that language reached its limit, really. It needed lots of tooling, it needed lots of extensions, and we really needed to use a real language instead. But the area we are working in has some slightly unique demands. So we have to be able to get stuff into production very, very quickly. And that means having a strong type system is really useful. Having an abstraction that meant the user doesn't have to think about concurrency is also really useful. So we experimented with various different languages, and we found that doing this in Haskell worked out really nicely.
Yeah, going back to the example about the software updates, I'm looking at the code there. It uses MapM, and I'm wondering, I thought MapM actually does everything sequentially. I'm wondering how it gets the concurrency in there. Is that something Applicative Do does for you? Or?
Right, so the question is, isn't MapM sequential? And the answer is, MapM uses applicative internally. So this wasn't true in the past, actually. It changed at some point when the applicative class was added to the type class hierarchy in Haskell. So MapM is defined in terms of applicative, and a bunch of other things are defined in terms of applicative as well. So they get to take advantage automatically of the implementation of the applicative operator in Haskell. I think I have a question.
Is there some sort of boundary or way to manage the life cycle of the cache?
The question is there a boundary or a life cycle of the cache? So we implemented, so in our system, requests tend to be quite short-lived, so we didn't implement a boundary on the cache. It's not clear to me exactly how you should do that. We certainly have a way to run things without a cache, we have a way to clear the cache, but the particular policy probably depends very much on your use case. And maybe you want to have a bounded-sized cache or something like that. But the problem is that as soon as you decide not to cache everything, you lose some of these nice properties. So you can't guarantee to have the complete record of all the I/O, and you can't guarantee to be able to generate a unit test and so forth. The question is, if there are pure functions in the do notation, do we cache those as well? And the answer is no. We do have a generalization of the caching mechanism called memoization, which lets you cache not just a data fetch, but a whole computation. We found that to be really, really useful. So you can annotate functions with a memo function, and it will record the result of that. So we use that for caching computation as well as data fetching. Any other questions? Okay. One here.
It seems like you could use this to write a good build system.
That's a really good question. So the question is, can you use this to make a build system? And the answer is yes, and I've done it. I'd be happy to show you later. Okay, I think I'm going to wrap up there. Thanks very much.